Hi, my name is Katie McShea. I'm a member of Marymount University's honors program. I'm a junior and a biochemistry major. Today, I will be presenting research that looks at the effect a chemistry case study has on students' understanding of chemical bonds. This research was conducted by me and my faculty advisor, Dr. Dina Jaber. To start off, I'll be providing some background information on the chemical compounds that were used to create the storyline for the case study. These compounds are known as perfluoroalkyl or polyfluoroalkyl substances, or PFAS for short. These compounds are produced by companies such as DuPont and 3M and are known for their unique chemical structure, which allows them to be hydrophobic or water repelling and lithophobic or oil repelling. These compounds are also extremely stable in the environment and cannot be broken down easily. If you look at figure 1, it shows the general structure of a PFAS compound. Most PFAS compounds have an 8-carbon chain, also known as the backbone, with most of the carbons being attached to fluorine substituents. These fluorine substituents on the carbon chain allow the PFAS compound to be extremely stable and also hydrophobic. In addition, PFAS compounds also have a functional group head, also known as an R group head, attached to the carbon chain. The functional groups that are usually attached are carboxylic acid, sulfuric acid, or phosphoric acid. And when these functional groups are attached, the compound has its lithophobic nature. PFAS compounds are generally used as surfactants and are in many products that are water and oil repellent, as well as heat and acid resistant. Some of the products that these compounds can be found in are floor waxes, textiles, and firefighting foam. In addition, PFAS have been manufactured for over 60 years, but over the past few years, PFAS have been receiving increased media attention for their adverse environmental and health effects. Since PFAS compounds do not occur naturally in the environment, they have to be synthetically produced. During the production of PFAS compounds, many derivatives and fragments are created. These byproducts are extremely hazardous and need to be disposed of, and are generally dumped into water sources that are located near manufacturing factories. These water sources end up contaminating local water sources, as shown in figure 2, where there right now are 43 known states with water source contamination. The dots in blue indicate contamination of local drinking water from communities that live near manufacturing factories. These communities with contamination have also experienced numerous health problems that are associated with PFAS exposure. Some of these problems are developmental issues in infants, compromised immune system, and increased risk of cancer. In addition, PFAS compounds cannot be broken down by processes such as hydrolysis or photolysis like other organic pollutants, and therefore continue to remain in water sources. Therefore, many individuals have filed lawsuits against DuPont and 3M. Besides their increased media coverage, PFAS compounds are also extremely relevant to college chemistry students. PFAS are extremely stable in the environment because of their chemical structure, specifically the carbon-fluorine bond. The carbon-fluorine bond is considered the strongest bond in organic chemistry, and we utilize this case study to help students understand different components of chemical bonding and understand why the carbon-fluorine bond is the strongest bond. The different components that we examined were different types of chemical bonds, electronegativity, atomic radius, bond length, dipole moment, and bond enthalpy. In addition, as shown in Table 1, we also compared the carbon-fluorine bond to other carbon-halogen bonds. In this table, we show the different values for carbon-fluorine versus other carbon-halogen bonds, specifically for electronegativity difference, type of bond, dipole moment, atomic radius, bond length, and bond enthalpy. Throughout the case study, we examine each of these factors and understand why carbon-fluorine has the values that it does and why these values attribute to bond strength. Furthermore, case studies are extremely important study guide tools for students. Case studies help students practically apply theoretical information to solve real-world problems and allow students to develop their analytical skills by promoting deeper learning. However, one issue that we found when creating our chemistry case study is that there is a lack of case studies in general for both chemistry and physics. Therefore, we wanted to develop a case study on PFAS compounds that allows students the opportunity to learn about chemical bonds, as well as the controversial disposal of PFAS compounds in the chemical industry. To conduct the research, all the participants for the case studies were students enrolled in the introductory chemistry course of the fall of 2020, and they all had received one lecture on chemical bonding. Upon completion of the lectures, students attended one of the 3 consecutive online workshops to discuss the case study. There was approximately 6 to 10 students in each workshop, and each workshop followed the same scheduling format. First, the students completed a pre-case study survey where they were read the consent form and they were asked a series of questions regarding components of chemical bonding and their understanding of these components. Then the students were split off into 3 separate groups and worked with the research leader in order to complete the case study collectively. When all 3 groups had finished completing the case study, the students then completed a post-case study survey where they were asked the same questions in the pre-case study survey, as well as additional questions about their opinions on the case study in general. Figure 3 shows what the analysis of each question from the pre and post case study looked like. In the figure, the question that we chose was, I can explain the concept of bond enthalpy. As shown in the first graph, which indicates the pre-case study survey, 45.8% of students disagreed with the statement, and 37.5% of students were neutral. However, when you look at the second graph, which indicates the post-case study survey, 62.5% of students now agree with the statement, and 25% of students strongly agree with the statement. These graphs were collected for all the different questions, and in regards to the main components of chemical bonding, 100% of students agree or strongly agreed that they can name 3 types of chemical bonds, which was a 20.8 increase from the pre-case study survey. 95.8% of students agreed that they could classify bonds based on the difference in electronegativity values, which was a 70.8% increase. 82.6% of students agreed that they could identify bonds that have a dipole moment, which is an 82.6% increase. 83.4% of students agreed that they could predict bond strength based on atomic radius, which is a 65% increase. 95.8% of students agreed that they could predict bond strength based on bond length, which is a 91.6% increase. And lastly, 83.4% of students agreed they could determine the strength of a bond based on bond enthalpy, which is a 75.1% increase. In addition, in regards to the students' general opinions of the case study, 95.9% of students agreed that the case study was a helpful study aid. 95.8% of students agreed it made studying chemical bonds more fun, and 100% of students agreed they would recommend the case study to others. Our next steps after this case study is that we will go back and we will make necessary changes to the case study based off of student feedback. In addition, we will then present the case study to the future students enrolled in the introductory chemistry course of the fall of 2021. We would like to thank Marymount University for their financial support of this work, and I would like to thank everybody for listening to this presentation. Thank you.